Hey everyone, welcome back to my channel. This is a place where we are unraveling the magic of artificial intelligence. If you are new to the channel, let me tell you that we are making a playlist on artificial intelligence named AI Builder. So make sure you access this playlist. And in this video, we are diving into the enchanting realm of uninformed algorithm with a spotlight on an algorithm that's like a path wizard known as Breadth First Search. So let's now understand the definition of Breadth First Search. So by definition, breadth first search, also known as BFS, is an algorithm used to explore a graph or tree level by level. Level by level is an important terminology for this BFS algorithm. So how does it work? Starting from the root node and moving towards its neighbor in a level by level manner. Let's understand this with the help of an example. Let's take this graph as an example. So as you can see, there are levels 0, 1, 2. So basically there are three levels in this tree and A is my root node. So after traversing the first level, I'll be getting A and then I'll be moving on to level 1 in which I'll get B and C. After exhausting all the nodes of level 1, I'll be moving to level 2 and on level 2, I'll be getting B, F, G. In BFS algorithm, I'll be traversing the tree in this manner. So now let's understand why is this traversal occurring in this order. So the main reason behind the traversal in this order is because BFS uses queue data structure as its frontier. If you don't know frontier, so frontier or fringe is a data structure that is used to keep the track of nodes that are needed to be traversed in the later phase of our search. So what happens? So whenever we explore a node in a graph or a tree, the direct children of that node are added to this frontier so that we can explore them in the later phase of our traversal. If you still don't understand, then I would recommend you to first watch the previous two videos of this playlist where I have explained frontier in detail. Then come back to this video. But this much explanation of frontier or fringe would be sufficient to understand the working of breadth first search, which I'll be explaining in the later part of this video. So queue is a data structure that follows the first in first out principle, ensuring that the nodes are explored in the order that they are added. Now let's understand what is this statement trying to say with the same example that we have seen just now. Let's again move back to the previous example. This is my root node A, and initially I'll be having A inside my root node. So the exploration of the search space starts by fetching an element from the frontier, which in this case is Q. So when we'll be fetching an element from this Q, what we'll be getting? We'll get the node A. So I'll be removing this from the fringe. So we are here. So I'll be asking the goal test, is this the goal? If the condition is not satisfied, I'll be exploring this A node and getting its children B and C. Here I'll be adding the children of A in left to right manner. So first B will go inside the queue and then C will go inside the queue. So this was the exploration of node A. Now again I'll be fetching an element from this queue frontier. I'll get B node. First, I'll be asking my goal test function, is this the goal? If the condition is false, as we can see, B is having only one child, D. So I'll be adding this to the fringe. After that, C will be taken out from the queue and explored. First, we'll be checking, is this the goal? If the condition is false, again, we'll be adding the children of C in this queue frontier. And this entire searching process keeps on going until we find a goal node or we completely exhaust the search space, meaning our goal is not present in the search space or goal not found. So that's how the BFS search algorithm works. So now it's the time to judge BFS algorithm on these four parameters, which are completeness, time complexity, space complexity, and optimality. But before evaluating BFS algorithm, you have to be familiar with three terms. First one is the branching factor, which is represented with B. The second one is the depth of the shallowest node, which is represented with D. And the third one is the maximum height of the search tree represented with M. So here talking about branching factor is the average number of children each node would be having in the search tree. The second one is the depth of the shallowest node. So the minimum depth where the goal node is found is represented with D. And the last one, M, it is the maximum height of the search tree, right? So this was all about these three terms. So first let's talk about completeness. Completeness means that if there exists a solution, will BFS be able to find that? So the answer is yes, if the branching factor B is finite. After completeness, let's now look on to the other two parameters, which are time complexity and space complexity. Here, time complexity can be understood as the number of nodes explored before reaching to the goal node. So that's why the worst case time complexity of BFS is B raised to the power D, where B is the average branching factor and D is the depth of the shallowest goal node, right? And secondly, if we talk about space complexity, so space complexity here can be understood as the maximum number of nodes in the memory at any particular instance, will be our worst case space complexity, right? And again, the space complexity is big O of B raised to the power D, where B is the branching factor and D is the depth of the shallowest goal node. This was all about time complexity and space complexity of BFS. Now let's jump on to optimality. So the first question is, what is optimality? So optimality means the algorithm finds a path to the goal node. Would it be a least cost path? This is the meaning of optimality. And the second question is BFS optimal? And the answer to this question is yes, under a condition that if all the step costs are identical. If you are unaware of step cost, it means that the cost associated with the edge. So here for BFS to be optimal, that cost for all the edges should be identical. Here BFS guarantees optimality because it explores the node level by level and it finds the goal at the shallowest depth. After evaluating our BFS algorithm on these four parameters, we'll be understanding the algorithm and application of breadth first search in the next video. So make sure you subscribe to the channel and thanks for watching this video.